Hi, my name is Manish Gupta, and in this video 209, I'm going to talk about depth anything, which is basically using large-scale unlabeled data to obtain a model which performs really well on depth estimation. Okay, so let's get started. Let's start by asking this question: what is monocular depth estimation? So as you know, when we take images, the world is 3D, but the images are 2D. And therefore, finding depth of every pixel in an image, how far it is away from the camera, is an interesting problem to solve. Here are 6 outputs from 3 different data sets that you see, using the depth anything model. So in the first row, you basically see the original images. These are 6 original images, right? In the second row, what you see are the depth heat maps obtained by running this depth anything model. Okay. So essentially, for example, since this table and chair are close to the camera, they are shown in warm colors, while things which are far away from the camera are shown in cold colors. Now, depth estimation can be solved in 2 ways: relative depth estimation or metric depth estimation. Of course, relative just tries to figure out relative distances between pixels in the image, while metric depth estimation tries to figure out exact depth in meters, in meters typically, right? So where this is applicable, well, it has several applications in robotics, autonomous driving, virtual reality kind of applications. Right? Why is this challenging? Well, there are several challenges. Some of those challenges are also highlighted in these images, as you can see. So in the first and the third image, you can actually see some low light environments, like how low is this lighting condition, right? Then the second and the fifth image, you can actually see complex scenes. So lots of people here and lots of buildings here in that senses. Right? Fifth one, you can also see another challenge of foggy weather. Fifth and sixth, you can also see ultra remote distances, right? So in some cases, this is not very remote distance, but these are, of course, very remote distances. Right? So this is challenging, and there is a lot of variation as well. So how is the depth anything model trained? Well, these folks trained depth anything model by initializing from the DynoV2 encoder. DynoV2 is a very popular model for semantic segmentation and image retrieval kind of tasks. Right? So, and the way they train this model is by using a combination of unlabeled and labeled data. Okay? So they basically want to make best use of a large scale unlabeled data. So therefore, they actually obtain a huge amount of unlabeled data. In fact, 62 million samples of unlabeled data from 8 different data sets. So lots of variety in them as well. Okay. They also obtain a large amount of unlabeled data, about 1.5 million labeled examples from 6 different data sets. Okay. So you see, I mean, there are several interesting specific properties of these data sets. Some of the data is indoor data, some of the data is outdoor data, and some of the data sets have a combination of both of them. Right? So the first step in their training is to essentially start with the DynoV2 encoder. And also the entire model is sort of the pre-trained semantic segmentation model, which has been trained to detect the sky region as the farthest region, right? You can basically say that the sky region is the farthest region with depth equal to infinity, or the inverse of depth is called disparity. So disparity equal to 0, right? And you initialize the encoder using DynoV2, and you train a large teacher model using 1.5 million labeled images. So first you use the labeled images to train a very large teacher model. Then you, of course, train a smaller student model based on a combination of labeled data and the pseudo-labeled 62 million set. So the 62 million unlabeled set is pseudo-labeled using this teacher T. And that's how you get pseudo-labeled data in that senses. And then you train the student model on this combination of labeled and pseudo-labeled data. Now, while training depth kind of models, essentially you transform the depth to disparity, d equal to 1 by t. So if t is the depth, d is the disparity. Okay, so t is the depth, d is the disparity, and you normalize these outputs from 0 to 1. So basically, you're trying to predict a target between 0 to 1 for every pixel in that senses. And when it comes to labeled data, it's basically trained using affine invariant loss. Okay. So let me talk about the affine invariant loss. It's computed using this formula. So affine invariant loss is computed per pixel, and then you take average over the pixels, and that is why you see height and width mentioned here, right? So basically, for every pixel, you have the ground truth disparity, and you have the predicted disparity, and you compute the affine invariant loss for every pixel and take the average. Now, how is this, I mean, the loss computed? Well, it's computed as a simple, absolute difference between the disparity values. How are the disparity values obtained? Well, they are basically normalized disparity values. So the predicted and the ground truth, both of them are normalized disparity values using some sort of a z-score normalization. But here, T of D, rather than being mean, is actually median. And S of D, rather than being the standard deviation, it's actually just the deviation from the mean, absolute deviation from the mean rather than the squared thing and so on. Okay. So that's basically how you compute the affine invariant loss over the labeled data. Now you have this unlabeled data which has been pseudo-labeled. You also want to basically make use of it so as to train your student model. How do you do that? Well, the way the student is trained in a robust manner is by injecting strong perturbations to unlabeled images. Okay. So the idea is that to the student, you basically inject very strong perturbations to unlabeled images and give that as input to the student. And the student is trying to then come up with an output while the teacher actually uses the original image without any perturbations. Okay. So to the student, you basically put up strong perturbations, and in fact, two kinds of perturbations: color distortions. Popular color distortions are color jittering and Gaussian blurring. And also you can do strong spatial distortion called as cut mix. Okay. Now, you see, I mean, color distortions are very obvious. You can do color jittering. So, RGB values, you can basically maybe, jitter them, move them by doing some, random perturbation within a range of, let's say, -10 to 10. Okay. Or you can add Gaussian blurring, right? So add white noise to the original image. But cut mix is a very interesting spatial distortion. So the way cut mix works is explained in this block. Okay. So the way cut mix works is explained in this block. You take two unlabeled images, U and UB, and then you take a mask rectangle. A mask rectangle basically means within the rectangle, the values are ones. Everywhere else, their values are zeros. And then this circle with a dot indicates Hadamard product, basically saying element-wise product. Okay. So the idea is that you basically obtain a noisy version of image A by actually, taking a rectangle in image A and replacing that with a rectangle from image B. Okay. So the idea is you make a noisy version of image A by taking a rectangle from, cutting out a rectangle from image A and replacing it with the same size rectangle from image B. That's what you do. Okay. And then the unlabeled loss, for this distorted image UAB is basically computed as follows. You give this distorted image to the student, S is the student, T is the teacher, right? And you give the original image to the teacher, and you compute that the affine invariant loss for the area within the rectangle in that senses, right? Now for the area outside the rectangle, again you give the original image B to the teacher, but you give this distorted image UAB to the student, okay? And then you compute the affine invariant loss. And of course, you basically take these two losses, and your total unlabeled loss is an average of the a weighted average of the two unlabeled losses, one within the mask rectangle and one outside the mask rectangle. Okay, so that's basically the unlabeled loss. So the student, as I mentioned, is trained using a combination of labeled and unlabeled losses. The labeled loss is that, unlabeled loss is that. Okay. Now, as another variant, basically they also train models which align nicely with the frozen Dino V2's features. Okay. So what they said is that, hey, identifying depth of various pixels in an image is very similar to semantic segmentation task. So how about actually taking features for depth anything model and taking features for the semantic segmentation model and ensuring that they're aligned with each other. Okay. So in some ways, sort of doing multitask learning so as to align those features together. And then of course, you'll basically have different heads to do, a depth estimation in that senses. Okay. So therefore, they align the features nicely using a frozen Dino V2 encoder. So they take the encoder features from Dino V2 and take the encoder features from the student model, which has been trained using the combination of labeled and unlabeled losses, losses, right? And the way they align the features is basically as simple as that. You take the feature vector from the student model. You take the feature vector from Dino V2 frozen encoder. For the size of the entire image, you basically compute the cosine similarity, and then 1 minus cosine similarity is the loss. 1 minus average cosine similarity is the loss. So basically, three interesting things in their depth anything model training. One, they use a huge amount of unlabeled data and therefore process things using distillation, knowledge distillation from teacher to student. Second, when they train the student, they basically train it on three interesting losses: the labeled loss, the unlabeled loss, and feature alignment loss. Okay. And the third thing, when they basically try to compute the unlabeled loss, it's not straightforward. They basically do distortions to the image, both color distortions as well as space distortions, especially using cut mix, so as to enable a very, very robust student model. Okay. Now, how does depth anything perform? Well, they perform several experiments. Many of them are in the paper. I'm just showing some of them. So they perform experiments on zero-shot relative depth estimation. Zero-shot basically means that you have pre-trained this model using, it's a student model pre-trained using labeled as well as, unlabeled losses, but then you do not really specifically train it specifically on that data. Okay, so essentially, and they do comparisons with MIDAS, another model, and depth anything. Of course, they are model variations, small, base, and large. Okay. So they took the MIDAS model with a VIT large encoder, and they compare it with their VIT small, VIT base, and VIT large encoders across 6 different data sets using 2 matrix, absolute relative error. So, this lower the better, and then delta 1, which is an accuracy matrix, so higher the better. Okay. So what do you observe? You observe that, of course, their model, the largest model, performs really well, much better compared to MIDAS. Hey, in fact, the base model actually performs better than their large model in most cases. Okay. So in most of those cases, the lower the better. So this is better, so the underlying ones are the second best. And as you see, VIT base 1 with depth anything is actually better compared to the MIDAS VIT large model also. Okay. Now, they also fine-tuned the models using particular data sets. So for example, in this case, they fine-tuned on the train set of NYUv2 dataset, and they tested on the test set of NYUv2 dataset. And again, they observe that their model performs really well across multiple accuracy metrics and multiple error metrics, okay, compared to several other models which also perform depth estimation. Okay. Lastly, they perform a very interesting experiment. They take an original image, they extract the depth estimation from that image using the depth anything model, their own model, and the MIDAS model. And then they basically try to use ControlNet as a model to synthesize, synthesize images using the depth estimation maps as a conditional generation, guiding signal. Okay. And what they observe is that, of course, as you can also observe, these images which are generated such that they're conditional on the depth maps obtained using depth anything model are way better compared to the images which are generated using the MIDAS generated heat maps. Okay. So even in this particular case, as you observe, this one is way better compared to the MIDAS generated or compared to the ControlNet generated image using MIDAS generated, depth estimation signal. So in summary, in this video, I talked about the depth anything model. It preserves rich semantic priors from pre-trained models like DynoV2. It is, of course, a model for robust monocular depth estimation. And essentially, it leverages a large pool of unlabeled images to train a very robust student model from a teacher model using strong color and space perturbation, especially the cut mix perturbation. Right? Experiments basically showed across several data sets that the model, depth anything model, has excellent zero-shot depth estimation ability. And also, when you fine-tune the model on specific data sets, it is a very good model for downstream tasks like metric depth estimation as well as semantic segmentation. Okay. Okay, that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.